Swayam Prabha. Digital India. Educated India.
What we will do is using this example of flow between two parallel plates, we will link all the concepts which we have discussed as we progressed from the linear momentum balance or the integral balance to the Navier-Stokes. Okay. So, we discussed about total stress, strain rate, Newton's law of viscosity and Navier-Stokes equation. Okay. We are going to link all these concepts. You will also understand the better the path we have followed. Okay. Okay. Now, let us do that. So, we will use this as usual this journey to the Navier-Stokes equation, of course, the destination reach slide. So, now we began with the total stress, okay, that is where we began. Okay. Of course, I will discuss only the fluid mechanics part. So, now we introduced viscous stresses, okay, represented by this viscous stress tensor. We introduced all the components of viscous stress tensor, normal and then shear. We also introduced the total stress tensor, hydrostatic stress plus viscous stress, just addition of minus p to all the diagonal elements. Okay. So, this is where we began with. Point is that they are unknowns, at that point they are unknowns, okay, and they are just variables. Now, what did we do next? We discussed about strain rate here, introduced velocity gradient tensor. So, now we can evaluate the velocity gradient tensor. Why is that? Because we now know the velocity profile Vx is equal to Vp by h into y, which means I can evaluate the velocity gradient tensor, the components of the velocity gradient tensor. Of course, because only the Vx is the non-zero velocity component, there is no element in the second row and third row. In the first row, Vx varies with y only. So, this alone has a non-zero value. So, let us look at that. So, 0 Vp by h, just partial differentiating Vx with respect to y, you get Vp by h, all other entries are 0. So, earlier once again we introduced as a physically meaningful matrix or tensor, namely velocity gradient tensor, but now we are able to evaluate it because we have found out the velocity profile. Okay. Now, then we introduce about strain rate tensor. This is the expression, these are the components of the strain rate tensor. Now, once again we can evaluate the components of the strain rate tensor using the velocity field which we have derived. Okay. So, what are the components? Vx is a function of y. So, this will be 0, dou Vx by dou x will be 0. In fact, all the diagonal components, anyway, Vy is 0, Vz is 0, they are 0. And then coming to the off diagonal components, this is 0 because Vy is 0 and this has a value dou Vx by dou y and then half, okay, and that is what we will see now, 0. Then this derivative is Vp by h and half of that will give you this entry in the strain rate tensor, okay, which is the strain rate by 2. And of course, we know strain rate tensor is symmetric and can also evaluate it. This term is also half Vp by h, all other terms are 0. This term is 0 because Vx is not a function of z and Vz it is 0, and this term Vz it is 0, Vy is 0. So, once again 0. Of course, you can write the symmetrically other entries as well. Okay. So, this is the strain rate tensor, where we have non-zero values for 2 entries for 2 of the strain rate tensor components. Now, what do we conclude? The normal strain rate, they are the diagonal elements, they are 0. Shear strain rate is not equal to 0. What is shear strain rate? This is shear strain rate. Remember, our that particular strain rate tensor component is shear strain rate by 2. So, V p by H is shear strain rate, that is non-zero. Okay. What does it mean? If you take a fluid element either horizontally or vertically, there is no rate of change of the length, and if you take 2 perpendicular elements, let us say at some time t, at time t plus delta t, they will come together. Why is it? The shear strain rate is positive, which means the angle between them should decrease. Okay. So, that is the meaning of these 2 values which I have obtained. One is of course 0, other is non-zero. Okay. Now, we also discuss about rate of rotation tensor, okay, and these are the components of the rate of rotation tensor. Okay. Now, of course, the diagonal elements are anyway 0 because it is antisymmetric tensor, and we can evaluate the other components using the velocity profile, and let us evaluate them. This term is 0 because V y is 0, and this can be evaluated, and minus and minus becomes plus. So, what we have is half V p by H, and we know it is antisymmetric, the rate of rotation tensor is antisymmetric. So, this term is minus half V p by H. We can also evaluate that because this is 0 and then minus of half into dou V x by dou y will give you minus half V p by H, and all other entries are 0, V z is 0, V x not a function of z, V z 0, V y 0. So, all other components of the rate of rotation tensor, they are all 0. Now, what do we conclude? Remember, this term represents rate of rotation. So, in our nomenclature omega dot x y, and which is not 0, which means it is a rotational flow. It is a rotational flow, and it is negative, which means the fluid element will undergo a clockwise rotation. Remember, we said clockwise is negative, anti-clockwise is positive. So, the fluid element will undergo clockwise rotation. Okay. That is the conclusion from here. Okay. Then we discussed about the Newton's law of viscosity, where we related the viscous stress to the strain rate, and we can do that as well here. The viscous stress tensor is equal to 2 mu into the strain rate tensor. We have used d for this, okay, and so substitute the strain rate tensor we found out 2 slides back. So, this was the strain rate tensor. So, just multiply by 2 mu, you will get the viscous stress tensor, and we can also evaluate the total stress tensor. As we have seen, just add minus p to all the diagonal elements, because it is minus p into identity tensor plus tau. So, to this tensor add minus p to all the diagonal elements. Okay. What is the big difference now? Earlier we introduced them as variables. Okay. Now, we are able to evaluate that. Not alone variables, they were unknown. When we first discussed viscous stress, total stress, they were unknown. Now, they become known. Not alone known, they are able to evaluate in terms of the velocity profile, because you know the velocity profile, you are able to evaluate the viscous stress tensor in terms of the variables which describe this particular flow. What are the variables which describe the flow? One is of course property of the fluid mu, other is the velocity of the top plate, other is the distance between the two plates. So, you are able to evaluate the viscous stress tensor and the total stress tensor. What is the other observation? If you look at the viscous stress tensor, it is just a constant, mu is a constant, Vp is a constant, H is a constant. So, does not depend on y, and that is what is shown here. The shear stress component of the viscous stress tensor, okay, or viscous shear stress does not depend on y, just a constant. Okay. This stress element we will discuss in the next slide. Okay. We also discussed about stress element in the beginning, okay, and we also discussed about stress vector. We will discuss about stress element in this example. Okay. How do you represent the stress element? How do you represent this total stress tensor as a stress element? Okay. We have done this in the very beginning of solid mechanics, okay, and of course, later on in fluid mechanics also. Now, how do we represent this? Okay. Now, if you look at the normal stresses, we have only pressure as a normal stress and it is compressive. So, we are representing it as compressive forces, and that is why the arrows are towards each other. So, on a positive phase, the force is towards the negative x direction. On a negative phase, the force is towards positive x direction, similarly in the y direction as well. So, that represents the compressive pressure forces. Now, coming to the shear stress components, this is positive, mu, V, P, H are all constants and it is a positive as well. So, on a positive phase, the force should be along the positive direction. So, if you take this phase, it is the normal to the phase is along the positive y axis. So, the force is along positive x axis, and for this phase the normal is towards the positive x axis and force is along the positive y axis. Similarly, these forces as well. So, now the earlier we discussed stress element, we used to have some artificially given values 30, minus 10, minus 15. Now, after evaluating the velocity profile and then going through the strain rate tensor, viscous stress tensor, total stress tensor, we are able to draw a stress element which represents the state of stress at a point in this configuration. Okay. So, now it is much more meaningful. Earlier they were just numbers. We did that all to have practice to understand what a stress element is. Now, we are really using it to tell about the state of stress in a fluid which is flowing between two plates, one fixed, other moving, okay. And we can evaluate that as well, okay, because we know mu, V, P, H all are all known to us. Okay. How do you interpret this? If you look at this shear stress, the fluid above the differential element pulls it to the right because that is at a higher velocity. So, that will try to pull it to the right, and plate below that is at rest, that is fixed. So, that will pull the fluid element to the left, and that is why you have the force in this direction. So, you have a fluid element and the top plate is set in motion, so is in moving. So, the fluid above that, if you consider fluid element here, fluid here it is higher velocity. So, it will try to pull the fluid element to the right, this plate is stationary and that will try to pull the fluid to the left, and that is what is seen there. Now, in terms of evaluating, we can evaluate the shear force per area, that is what our shear stress tells you, and shear force acting on bottom face of fluid element. Remember, always our viscous stress, total stress were with respect to acting on the fluid, So, shear force per area, which is our shear stress acting on bottom face of fluid element, is of course this mu V p by H, and what is the direction? It acts along the negative x axis. Okay. Fluid at the bottom plate, because the plate is stationary, the plate tries to pull the fluid to the left. So, shear force acting on the fluid element is towards the negative x axis, and of course, shear force acting on the plate is same magnitude mu V p by h, but along positive x axis. Okay. Fluid is trying to pull the bottom plate towards the positive x axis. Okay. That is why shear force per area acting on the plate is towards the positive x axis, okay. A bottom plate to the right, okay. Of course, due to viscous effects. Okay. In one way, what we have done is gone through a full cycle, I would say. Okay. We started with stress, went to strain rate, went to Newton's law of viscosity, derived the Navier-Stokes equation. Now, having derived the Navier-Stokes equation, we applied that, found the velocity profile, and then we found the strain rate, applied the Newton's law of viscosity, and found out the viscous stress and total stress. So, we have gone through one full cycle, I would say, okay. And that is what is shown here also in terms of our journey slide. We discuss about viscous stress, total stress, then we discuss about strain rate, related viscous stress and strain rate through Newton's law of viscosity, substituted in the linear momentum balance to derive the Navier-Stokes equation. Now, use the Navier-Stokes equation, found out the velocity profile. Once I know the velocity profile, I can know the components of strain rate tensor. I can find out the viscous stress tensor components using Newton's law of viscosity. Of course, it means this becomes known. Of course, we can draw the stress element as well. So, in one way, we have gone through a complete cycle, and that is what I have represented here. Total stress, then strain rate, then Newton's law of viscosity, then Navier-Stokes equation, then the velocity profile. Once you know the velocity profile, then find strain rate, use Newton's law of viscosity to find the total stress. Of course, I would not say perfectly cyclic, but these arrows does not mean one goes to the other, but we have gone through the cycle in the forward direction and once again in the reverse direction. Okay. When we went in the forward direction, they were all variables which aided us in the development of the Navier-Stokes equation. We kept on introducing physically meaningful variables, for example, viscous stress tensor, total stress tensor, strain rate, and then the Newton's law of viscosity. They were all expressions which helped us in deriving the Navier-Stokes equation. Okay. Following that path, we derived the Navier-Stokes equation. Okay. Now, once we have derived the velocity profile, we can evaluate all the variables which we have introduced. Okay. For example, dou v x by dou y was a derivative. Now, we can evaluate dou v x by dou y, okay. And then physically meaningful variables like the strain rate, and then the viscous stress tensor, and then you can also show the stress element, etc. Okay. So, so this one way, this helps us to understand the path we have followed and why we followed that.